HVZ reaction. What is the expansion? H means Hell, V refers to Volhard, H-A-R-D, Volhard, Z refers to Zelinsky. Hell-Volhard-Zelinsky reaction. This reaction is called HVZ reaction. Simply is called HVZ reaction, but the actual name is Hell-Volhard-Zelinsky reaction. Students, what is the use? This reaction will carry out halogenation at the alpha carbon. So it's a reaction called alpha halogenation. We call this reaction as alpha halogenation of carboxylic acid. Alpha halogenation of carboxylic acid. Okay, what is alpha halogenation? You know very well. Carboxylic acid attached to a carbon, and that carbon, right, is called alpha carbon. If this alpha carbon contain at least one hydrogen, then you can replace that hydrogen by a halogen atom. And this is what we call as alpha halogenation. So for HVZ reaction, what is the requirement? The requirement is this: you need at least one hydrogen at the alpha carbon, right? At least one hydrogen atom must be present at alpha carbon. At least one hydrogen atom should be present at the alpha carbon. Okay, and what is the reagent we add? Students, this is the reagent we add. Okay, we put red phosphorus plus halogen. Okay, we add red phosphorus plus halogen. Okay, and followed by hydrolysis. So first step is red phosphorus plus hydrogen, and second step is hydrolysis. Okay, so let me write the reaction here. I'll write the reaction. So I'll take a carboxylic acid. First I'll write a general reaction, student. I'll take a general reaction. So this is carboxylic acid, and this carbon is alpha carbon. Alpha carbon now contain hydrogen. Okay, now what I'm going to do, first I'll treat it with phosphorus with some halogen, right? Say chlorine. I'll put red phosphorus plus chlorine. So what will happen? In the first step, you will get one hydrogen is replaced by chlorine, and here the acid becomes COCl. Now if you carry out hydrolysis, okay, what will happen? This chlorine will come out, and you will get back the acid. You will get back the acid here. And now what we actually did here is we have replaced an alpha hydrogen by an halogen atom, and this reaction is what we call as HVZ reaction, Hell-Volhard-Zelinsky reaction. Take down. For this reaction, at least one alpha hydrogen must be present at alpha carbon. Right? Now how this reaction takes place, students? Observe the mechanism.
Sir, 1 minute finish.
Mechanism.
Sir, 1 minute finish for the previous
Yeah.
Yes, sir.
Now observe this, student. What is the mechanism? First step is this: phosphorus reacts with the halogen, form phosphorus trihalide. Okay, now I took chlorine, so let me write with the chlorine. With the chlorine, it forms phosphorus trichloride in this reaction. Then in the second step, carboxylic acid, the example that I have chosen here is RCH2COOH. Okay, I took this carboxylic acid here, so it will react with the PCl3. Listen, what PCl3 will do, it will replace this OH group by chlorine. Okay, this reaction is well known, right? PCl3 will replace OH group by chlorine. This OH group may present in alcohol or carboxylic acid, whatever it is. If you have OH group and if you want to replace that into chlorine, then this is the best option. So this is one of the option. Okay, RCH2, you'll get COCl, right? Actually, you should take 3 moles of this. It will react with 1 mole of this, so you'll get 3 moles of this product plus H3PO3 is formed as the byproduct. Right, now students, I'll take this compound. This is the third step. This compound I'll write CH2 like this, RCH with a single bond CH. Then we have CO group and we have a chlorine atom. This will tautomerize. Students, observe carefully. This will tautomerize. Tautomerization takes place. How? This hydrogen comes out as H plus and this bond will migrate here, so you'll get a double bond, and this pi bond shifts to oxygen, so oxygen gets O minus charge. Okay, it gets minus charge, and this H plus get attached with that minus and form OH. So you will get this compound RCH double bond COH, it become OH and chlorine. You'll get this. Now to this we should add chlorine. I'll write here, to this we should add chlorine. This is addition of halogen to alkene type of reaction, so we will add chlorine. So what will happen if you add chlorine? This pi bond will attack the chlorine, so one chlorine comes out as Cl minus. One chlorine comes out as Cl minus. So one Cl minus will come out, and this chlorine get attached to one of the doubly bonded carbon, and the other carbon, if this chlorine attached to this carbon, the other carbon get positive charge because it is electrophilic addition. So you get RCHCl, double bond becomes single bond, and you'll get a positive charge on this carbon. This positive charge is stabilized by resonance because these atoms have lone pair, so this positive charge is more stable. Therefore only this product will get. Listen, you have two options here, student. Actually you can add chlorine to this carbon or chlorine to that carbon. If you add chlorine to this carbon, you will get positive charge on this carbon, and that positive charge is stabilized by resonance. Whereas if you add chlorine to this carbon, you will get just a secondary carbocation which is not further stabilized. Okay, so only this carbocation will is formed. Then what's the next step? The next step is this H hydrogen comes out as H plus, and this bond will go back here. Okay, and you will get this positive charge get neutralized. So you will get this compound, that is RCHCl. Okay, single bond COCl. You will get this product. Okay, so if you add red phosphorus with the halogen, you will get this compound. Then this compound undergo hydrolysis. Okay, chlorine will be replaced, so you will get RCHCl COOH. Take notes. Take down this. Now students, observe this carefully. In this reaction, the halogen that you use, it may be chlorine or bromine or maybe iodine. You can use chlorine, you can use bromine, you can use iodine. With chlorine, the reaction occurs faster. With bromine, the reaction occurs smoothly. Smooth reaction will occur. With iodine, the reaction is extremely slow. Very, very slow. Very, very slow. So normally we won't carry out the reaction with iodine. We use normally chlorine and bromine. Okay, take note. This is another important point you should carry out. You should keep in mind. Now let me write a few examples here. Examples for HVZ reaction. Okay, so I'll take this carboxylic acid CH3 CH2 COOH, right? I'll put red phosphorus plus chlorine followed by hydrolysis. Okay, see here carboxylic acid is there and this is alpha carbon. Alpha carbon now contain hydrogen, so definitely the alpha halogenation will occur. Okay, so what will happen? Replace one hydrogen from alpha carbon by chlorine, because you are adding chlorine. So what's the product? You will get CH3 CH Cl, and further hydrolysis there, therefore you will get the acid back. Okay, you will get this product. What's the name of the product? This is carboxylic acid, carbon number 1, this is carbon number 2, so 2-chloropropanoic acid. Okay, take down. Second example. See this, student, this is very important. I'll take benzoic acid and I'll put red phosphorus plus chlorine, further hydrolysis. See, student, in this case we have carboxylic acid and this is alpha carbon. This is alpha carbon, but there is no alpha hydrogen present, because in benzene, you know very well, each carbon has one hydrogen, but here that hydrogen is removed. Instead of that, this acid group is attached. So in alpha carbon there is no hydrogen present, therefore HVZ reaction does not occur in this compound. For HVZ reaction to occur, alpha carbon should contain now here see, student, we have carboxylic acid and this carbon is the alpha carbon. Alpha carbon has one hydrogen now. Yes, there is an hydrogen, so definitely the reaction will occur. So if I put red phosphorus plus chlorine further followed by hydrolysis, what will happen? That alpha hydrogen COH remains as such, that alpha hydrogen is replaced by an halogen atom, say chlorine. Okay, take note. This is what we call as HVZ reaction, Hell-Volhard-Zelinsky reaction, which will carry out alpha halogenation in carboxylic acids.